Okay. Zoom, we're recording. Seems that we are happy. Questions about anything? There is still. Okay, let's start with more trees. We are desperately in a shortage of trees, and the trees that we are going to cover in the first, 15 minutes of the lecture will be with the most confusing names. They are called multidimensional range trees. And it's so confusing because we had ranges in quad trees, where we talked about a query, and every node has its own range. And then we talked about the ranges in KD trees and in B trees. So multidimensional range trees is not KD trees, nor they are quad trees, not R trees. Different animal. Hello? 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 Okay. I want to speak about data structure that can take a set of points, all of them, data structure that takes a set of points, set of keys, and all the keys at the moment are all on the x-axis. So it's all in one-dimensional data structure for the time being. So I need a data structure that takes a set of points all on the x-axis and think about them for a while. It will be a bit time to pre-process as usual. As usual, the name of the game is that you're taking the data, meditate on it, pre-process it, spend some time in the pre-processing and spend some memory, and then I bombard you with a sequence of queries, and for each query I want an answer fast. So let's now be the points on one-dimensional, and the query that I'm going to give you is I'll give you two values, mu and mu prime, x and x prime, and I want to know who are all the keys between x and x prime. No y in the game for the time being. Who are all the keys between mu and mu prime? Keys that are larger than mu but smaller than mu prime. And we don't need to think very hard about this problem. We are just using any search tree or skip list. By the way, skip list will be also happy to answer it, but I'll talk about trees. So we are taking any binary search trees. And to be honest, array will be good, but I still want it as a tree because of future application. So I'll put it as a tree. And now you go make your query. What you surprised me with is you told me what is mu and mu prime, and I'm doing search of mu in this tree and search of mu prime in this tree. And I want you to look very carefully about how the search path looks like. Here I have the tree, and here I just have zoom in into this tree. So both when I'm visiting mu and visiting mu prime, I start at the root. And then I check, hey, root, are you larger or smaller than mu? Maybe the root is larger, so I go to the left, right. And both when I go for mu and mu prime, my path at the beginning maybe goes together, both for mu and mu prime, until there is some node that these two paths split. Makes sense, right? This node where the two paths split might be the root as far as I can. That's fine. It might be the root. However, after they split, here is my path to mu, And here is my path to mu prime. And now I highlighted a bunch of trees in this figure. What is special about these trees? When I'm going to mu, these are all the right trees or nodes where I branched left to mu. And after the split, I'm looking for mu prime. And these are all left subtrees of nodes for which to get to mu prime, I branch right. Was it too confusing? Here is my first path. Here is my second path. Here is a split point, V split. Here is one such subtree. So there is some value here, and I'm looking at one of the subtree, where for this node, I branch right. Here is another node I branched to get to mu. I branch left from, I highlight at this node, y, I lost y, and no, I didn't lost y. This might be, this node will be a q. This node might be q, and here is this subtree that I highlighted over here. So from q to get to mu, I branch to the left, but to go to mu, I branch to the left. But here is one of the subtrees that are on the right. And analogously, to get to mu prime, here is one of the left subtree of a node from which to get to mu, I go to the right. That is, my search path doesn't go into any of the subtrees that I highlighted. And now I look very closely at all the nodes that are stored in this subtree. Let's x0 be one of these keys that are stored in this subtree. So what do I know about x0? Every value x0 over here, it's larger than q, because to get to the subtree, I'll go to the right. So it's larger than q, but to go to, it's larger than mu. It's larger than, it's larger than q, and q in turns is larger than mu, because to go to mu, I went to the left from this subtree. Everybody here is larger than q, which is in turns larger than mu. So anybody here is larger than mu. What happened about mu prime? To go to mu prime, from the split, I went to the right. Everybody in this subtree, to go to this subtree, I had to go to the left. Conclusion, was a very convoluted way to say, everybody in this subtree is in the range between mu and mu prime. Everybody here, I don't need any further checks about anybody in this subtree or in this subtree or in this subtree. And same goes the other way around. Everybody here is in the range of mu, mu prime. How many subtrees do I need to visit in this way? At most 2 log n. 2 log n on the right branch, and log n on the left branch, log n to the right branch, altogether log n such subtrees. And a few definitions that will help us in the future. For every node v, I will look at p sub v. Sometimes just for font size, I'll call it p parentheses v, mean the same thing. P sub v are all the keys, all the data points that are stored in this subtree. Okay, all the little points that are stored over here. Cool. And sometimes I'll call it canonical subset of points. Right. You see a lot of canonical subset over here. Look at any of the trees. There are some subtrees that I highlighted, but if I search for other values, it will be different trees that will be highlighted. Every root of every node defines its own subtree, and in this subtree there is a canonical subset. Confusing when I'm saying it like here, it will be cleaner as we are continuing. Time analysis for this one-dimensional subtree. query time might takes that if we are returning all the points and I print all the points, it will take linear time. Theta, remember, at most order n and no less than omega of n in the worst case. But that if I print all the points, and we don't really need the tree, but with this tree, what do? I get to this subtree, print all the points in it. Go to this subtree, also in range. Print all the points of it. Of course, I need to do this find of mu and find of mu prime before, but once I know these two paths, and I know where is a split, everybody in this subtree is fine. So how much time does it take me to print all of them? There is another one little observation that I need to tell you. Is there any node, any key that lives in this subtree and in this subtree as well? If I'll ask you if there is any node that lives in this subtree and any node that lives in this greenish subtree rooted here, definitely this node lives in both of them. They overlap quite heavily. But these two guys are disjoint. Nobody here, there is no key here that is also in here, because everybody here is smaller than the split, everybody in here is larger than the split, all disjoint. The same goes for, let's get rid of this greenish guy. The same goes for this subtree and this subtree that is also in range, because I'm below the split point. Nobody that lives in both these trees. They are separated by some node. So how much time does it take me to print everybody in here and everybody in here and everybody in here, since they're all disjoint? It's just the output size. How many points you have in the range. I don't tell you anything so far that you don't know. Log n plus k, where k is the number of points, where the log n comes from the two search and the number of subtrees that you generated. If you just want to know, by the way, how many points there are in the range, then you know log n would just keep a counter at the root of every subtree, telling you how many nodes are in this subtree, and you're just printing how many. To answer the question that you are all hesitating to ask, there is still a student that didn't take the midterm, so I'm not talking about the solutions, etc. Hopefully, by Thursday we can discuss the midterm more freely. At the moment, yeah. Okay, so that's why I avoid this subject. Okay, so we have these canonical subtree that you're still not sure what they are exactly, but every subtree here forms this canonical subtree. Okay, now when we finished solving in a very convoluted way this problem of 2D, right, an array with a counter of each node would be enough, but we are done with the one tree part. Let's talk about two-dimensional queries. And I want to know who are the points. I have a set of points that are all living in the 2D space. Right now we'll talk about the 2D space. Think about them, pre-process them, so that once I'll tell you about a query region, you can tell me who are the points that lives inside this query region fast. Okay. Pre-process them, meditate on them. I'll give you a query point. Tell me who are the points that lives in the query region fast. That's our goal. And your answer should be use quad trees or R trees or KD tree. All of them can answer this part. But what was the best one, the best time to answer a query that we've seen out of all the three trees that I mentioned? KD tree, quad tree, R tree. Give you a hint, quad tree and R tree didn't come up with too many guarantees about performances. They will be saying, yeah, they're good in practice, actually, extremely good in practice, but if you are a theoretician, that really has nothing to do but trying to think about the worst case input and the worst case queries that might appear. They have a pretty lousy performances in maybe unrealistic scenarios. So KD3, where the query in 2 dimension was, again, reasonably much smaller in practice, but square root n in the worst case. And remember the argument, why did it happen? Because we ask if we only need to visit nodes that are somehow cut by the query region, and such nodes are only square root n. We meditate on this result for the KD3 quite fast. So now with the 2D range trees, I'm willing, yeah.
So does that mean it gets better in higher dimensions?
No, nothing gets better in higher dimensions. It's, I think, quite universal. In higher dimension, it would be n, 1 over d, n to the power of, that's a query, the worst case query time. It's not that people are not using astronomy projects that I was involved in all over science. People are using very successfully KD3s for all types of queries, and they are doing well because data is not created by obnoxious theoreticians that tries to think about the worst case. Luckily for all of us. But if you're asking what is a guaranteed running time, that's the one. So in 2 dimension, it would be n to the, that's a query time. It will be n to the power of 1 over d. OK, who remembers the space? Somebody else. Space of KD3. How much memory do we need? How much memory? How much of my file do I need to, how much of my memory do I need to dedicate to store a KD3 on endpoints? Order of, no, I don't, ignore constants. Order n. In any dimension. We split by this, we split by this, we split by this, but every point will be, we essentially build binary trees all together. The dimension just said, how do I partition, but I always split in the median, either by x or by y or by z. So the memory is linear. OK, now what happens if I don't like these numbers of either either order of square root n in 2 dimension or in higher dimension this, but I want a better query time. Answer is it's going to cost you. Cost in memory. But you cannot do much better than this if you insist on linear memory. But what if you are willing to spend a bit more? That's where we are going. So query is always a rectangle. No guarantees about anything that is not axis parallel rectangle. Orthogonal rectangle, that's my query, defined by all the points which are between x and x prime, all the y's which are between y and y prime. And okay, I'm not trying to use it for other types of queries. Triangle, not included, no guarantees. How am I going to answer such a query? So I'll think about my rectangle, and I'll think first about the x dimension of this rectangle, the x coordinates, and I think about all the data points that you don't see over here. And this defines x and x prime, defines an infinite slab. All the points, no matter what or y, between x1, I used x multiple times, so I called the left point, x1 and x prime. x1 is just what x used to be, but there is other x's that are appearing. So let's meditate on, let's find the data structures that can answer this infinite vertical slab queries. Who are the points that lives inside this slab? Well, if all I care is about this slab, then the y dimension doesn't play any role. So let's just use the data structure that we had earlier. Right? Y dimension, for a moment, I ignored. Let's use the previous tree. Use the previous tree, we know that it works. If I care about the slabs, not about the y value at all. So how do I actually answer what is the data structure that I prepared for these rectangles? I start by building the same tree on the x dimension. I take all the points, all the data points in 2D. I look at this point, xi, xi, yi. I forget about the yi, so I'll project this point on the x-axis. The same goes for any data points, and build on them the same tree that I earlier had. And now there is a cute observation that I want you to do. I'm doing now, in this tree that I had before, a search for, we called it x1. It used to be mu a few slides before. I'm doing search for x1. I'm doing the search for x prime. I look at one of these canonical subtrees that I had earlier, and look at all the points inside it. What do I know? Every point inside it, in terms of x, it's a two-dimensional point. It is point xi, yi that I had earlier, but as far as x is concerned, it's in the right range. It's between x1 and x prime. If it's in my query region or not, that's a question about the y, but definitely, as far as x is concerned, it's inside the range. Each one of these subtrees, I don't need to check any point in each one of these gray subtrees. Each one of them is inside my range. OK. So what am I going to do next? First, if the second time that you see it, that's calligraphic T. Sorry, calligraphic T. Maybe it has different name. Tell me if you know. I know it as calligraphic T. So remember, every node of my main tree, I'll call it just T. Every node V in my main tree, it has a set of points associated in this subtree. Also remember, this subtree, or the whole T, is sorted based on x. What do I do for each and every node? I look at the set P of V, all the points that lives in this subtree, sorted by x, and I copy them. And I build a tree for them. For every node V, no matter what this V is. Remember, I don't know what's a query. Query is not given to me yet. So I build T, all the points sorted by x. Pick every node V, look at all the nodes in its subtree, all the points in its subtree. Ignoring the, remember, so far I just cared about the x value of these points, sorted by x. I look at this set of points, and I copy them, and now I build a new tree. I called it T of V. In the textbook, it has its T associated subtree with V. I just didn't want it to, the font became too small, so I just call it T of V. And what is T of V? This is V. It's for this particular node in the main subtree. It's my main. T of V, as you are guessing by now, contains all these points. It's actually a search tree containing all these points, but sorted based on y, as expected. So there is a whole forest. Let's jump one slide for a moment. There is a whole forest that I'm building right here. So you see the main tree. Here is the leaf sorted by the X, all the data points sorted by the X. Here is a search tree. And I pick each and every node in this tree. Pick this node. It has a left child. It has a right child. But now it has a new pointer. And the new pointer points to a subtree. The subtree can be quite large. Who this tree contains? It contains all the points over here, but the gray tree is sorted based on Y. So the root has a pointer to one more tree containing all these points, but now sorted by Y. And so goes for each one of the subtrees. Okay. Once again, just to show the slide, I look at the root, I look at the left subtree, the root of the left subtree, the root of the left subtree, who is P of this node. This is all the points starts here and here. Take all of them. And this node, the left of the root, have a pointer to a subtree that contains the very same points, but now sorted by Y. Going back one slide. How do I perform a query now? So remember, how do I perform a query? I go to the main tree and perform a query with X and X prime, X1 and X prime. Right? Only the X values. What I got as a return? As a return from performing the query in the main subtree, this will be T, the main tree. I perform a query by find of X, perform another query by find X prime, ignoring the Y and the Y prime. And I look at these paths. And I look at one of the nodes of this path where my path, I'm below the split point, and my path to find X branches left, and I look at one of these canonical subtrees. All the points here are between X and X prime. What is this subtree? It's associated with yet another subtree that contains the very same point, but sorted by Y. I don't care about are the points here. I don't care anymore about X value. They are all inside the slab. They are all inside the slab between X and X prime. All I care is, do they satisfy the Y condition or not? How do I do it? Go to the subtree, T of V, perform a query by Y. You already if you are inside the subtree, then you already passed the X test. You're between X small and X large, X1 and X2. Where I just need to check who are the points that satisfy the Y condition. Cool. And so I find the subtrees of T prime. All I need are a collection of pointers. There are order of log n, to be precise, 2 times log n such subtrees. Go to each one of them, once I know the roots. And for each of these roots V, perform a search of TV with the Y interval. OK. So query algorithm, select the order n roots of subtrees, and perform one-dimensional range query used to report all the points in this subtree in each one of them. But one-dimensional range query, first on the whole X values, collect all the subtrees, all the roots of the subtrees, log n such subtrees. In each one of them, perform a 1D search with a y interval. How much time are we spending for the query? For every node v inside the range, we are spending log n time for the search in the y value, plus k of v will be how many points do I squeeze from the subtrees that are relevant. Maybe from one subtree there are a lot, another subtree there are less. When I sum up from each subtrees, how many points did I print? Sum it all up. They're all relevant and none appears twice, all in the range. So k is the number, the output size is the number of points that I report, that I collected from all this. How many log square n many subtrees? Why log square n? Because where did the log square n comes from? Because from the main tree, I collected log n trees, order of log n trees, and in each one of these log n trees, I performed a search with the two paths, now with a y and y prime, which takes another log n. So it's log n times log n. Okay, and spend linear time. If you just cared about counting how many points there are, and you do the same trick of every node in each one of the tree keeps a counter, then you get rid of this k. It will just be log square n, no question asked. Questions so far? Everybody cool with this? What about the space requirement? OK, that's our weak point. I look at a point P. One of my data point P. It's stored in a tree of itself. It also stored in the parent of this tree. I needed the copy in the parent of this tree, parent of P. I also need to go to the grandparent. And this P will be stored at the subtree rooted at this guy. Subtree rooted of this guy all the way to the root. So every node P is stored in log n many trees. So the space requirement, and it's actually theta of n log n. So if I do a search in one tree, then theoretically there are tricks that can help me do a more efficient search in another subtree. So I can transform the log square n into log n. Okay. So instead of log square n, I can go down to log n. A bit interesting. It's theoretical because it's really the constant that you're paying, and the complication doesn't worth the effort usually. So I highlight it's recommended. We kind of discussed it, but take a moment and discuss what's the good thing about here, what's bad thing about here. We kind of cover it, but I'll give you a moment to KD tree versus a 2D-range trees. Each one has weaknesses and has strong points. It's 5:30, and you all look pretty beaten up. I'm sure that you had plenty of other deadlines, but yeah. Try to get a moment of adrenaline, talk to your neighbors, tell me compare KD tree versus 2D-range trees. You're not, yeah, well, I'm talking to,
That's fine.
yeah. So let's get, other. If I have, okay. It's a bit.
How easy is it to augment the range tree?
Formally, we don't call it augment. You mean the counters? Well, every node we just thought how many nodes there are. We didn't look at it from in terms of insertion deletion, but pretty much insertion. Yeah, it's a good point that these 2D trees. It's actually an excellent point. Is kind of easy to handle for insertions of points, at least until we start with a balancing thing. Then if I just want to insert like in every normal binary tree, that is, let it hang on the leaf and not worry about balancing, then it's easy to do insertion. If I want to do deletions, then again, if I think about AVL trees or red, black, or all of the above, there are rotations that makes life annoying. So instead of all the rotation and such, what practically people do is lazy deletion. Lazy deletion just says, let's talk about lazy deletion. It's an important technique by itself. Thanks for bringing it up. I just mark each node by itself. And now I have my whole subtree. And in my whole subtree, here in my whole tree, here is one subtree. And I keep track of how many nodes. N of V is how many nodes. And I'll also keep track of M of V. M of V will be number of deletions. How many nodes in this particular subtree are deleted? And when I'll decide that the number of deleted points in this particular subtree is more than the number of live points in this particular subtree, I'll just build this subtree from scratch. Not worry about rotation and such. Make sense? That's a lazy deletion. I don't need to build the whole tree from scratch. I can mark it, and that practically works much better than worried about the insertion deletion. But of course, if I delete it from several subtrees, and in each of them it needs to be marked. Yeah.
So what if you're not necessarily deleting, but the points are moving? You have something
Fantastic point about data structure of moving objects. Good research project. My patent from IBM was coming because when I was doing it, we were worried about you want an alert to your cell phone every time that one of your friends from a list of friends is at some vicinity near you. And we have a lot of moving points, and we don't want to repeatedly check between every pair of points what's the distance between them. Lots and lots of walks after, lots very. But I'll tell you what the method that works very well for us was to say, here are 2 points that I want to know if they are close to each other. What I'll do is compute the bisector, compute some safe area over here, and as long as this point did not move beyond it, and this strip between them is static, it's not going to change. And actually what I cared is convex hull of these strips that are created, and as long as this point Pi is not inside this strip, then Pj does not need to know about it. But it was a, and I'm not trying to say that that's most, that theoretically that's the best, but, and then you can say strips are mostly either horizontal or vertical. It's a good approximation, and we keep them into separate list, and it works very elegantly as a good approximation. But yes, there are lots and lots of work about, and I can send you to a list of reference that tries to squeeze a theory behind it. Because you need to ask how many are they moving along straight line, constant velocity or not. Very interesting, also very interesting in the case of vehicles, vehicle-to-vehicle communication. So, so maybe it was longer answer that you were that you hope for. Anyhow, I didn't hear too much communication, but somebody spit it out. KD tree versus 2D range trees. What's bad about the 2D range trees? We said that a query takes log square n, which you can squeeze into log n, which is pretty much the optimum. Plus, if you want to print the points explicitly, it will take constant per every point that you print. So it's close to optimum. If you're using this trick called fractional cascading, then you can squeeze it into log n. Without this trick, it's log square n. It's close to optimum. So it's actually the optimum with a log n. So what's bad? Why are we wasting time about KD trees? Space. No, I mean, it means that I have 10 gigabytes of data for the points, and now I need to have extra memory of log of 10 gigabytes for this trick. If you can afford it, of course, great. If you cannot afford it, then it's fine. But, yeah. So to perform a query or to build it? A good point, I didn't mention it. If you keep them sorted by x and by y, it's n log n. It's not hard to see, it's n log n. Trivially, it will be n log square n. So pre-processing, straightforward, no tricks at all. It will be theta of n log square n. And you can get rid of one log, and one log will be there no matter because we need to sort them somehow. So it's still n log n. So one cute thing about 2D range trees is orthogonal queries in d dimensions, say 3 dimensions. Again, only orthogonal. Not circles, no guarantees, not tilted boxes, orthogonal. Axis parallel, I have interval in x, so I'll use my main tree to satisfy all the points that are in the, now it's kind of 3D slabs, all the x's between x1 and x2, which in turn points to another tree that is built on all the y's that are okay in terms of x. Now I need to search for y, which in turn points to another tree that built all the trees that are relevant for z. So in 3D, the search will be log cube of n. Everybody, I hope, understand where the log cube is coming from. If you understand the log square, then now in the main tree, you generated log n canonical subsets. In the second level, each one of the log n trees that you created now has log n subtrees, 2 log n subtrees that needs the search that satisfies the y is in the correct values. So far you are done with log square n many trees, and now you need to check each one of them to see if it's in the correct dimension of the z. So, so that's where the log cube is coming from, and as before, we can get rid of one log. And the space requirement in the D space is, without tricks, it's log to the dn plus case. Sorry, that's a query and the space in 2D is log square n, and that will be in 3D, and in D dimension, it will be if I live in RD, in the D-dimensional space, the memory is theta of n log to the d minus 1 of n, log one-dimensional s. So of course, n should be really large. That log cube will be smaller than n itself. Okay, while KD3 that give you that practically works is linear in any dimension. Okay, so why am I teaching it? Because it's theoretically so cute, because it will give us new insight about the data structure, because it introduces this idea about the canonical set, that instead of complicated query, I can break it into a few criteria and use for each criteria its own type of search and getting just collection of canonical subsets. So there are a few ideas here that are transferable to many other problems. Okay. Any questions about the KD, about the range trees, 3D? Okay. Let's get back to trapezoidation, and I'll show you a data structure that works for finding where we are in a general map. We already talked about trapezoidation, and now I wanted to have a check mark about these topics before moving to the next part of the course. That will be more approximation algorithms, less introduction topic, less undergrad topic, more approximation algorithms that I find much more important to introduce. The real world is careless about, to be honest, about the difference between n and n squared. The real world is rather care about nice theoretical results, or care about moving from exponential time of n to the power d, which is, for example, the case of Voronoi diagram, into linear space or linear query time, which is a case of approximated Voronoi diagram. And there are many such examples where the difference is from exponential down to almost linear. That's probably a bit more applicable for other problems. Okay, point location. Still in the very non-approximated, very concrete space, you have a map. You are preprocessing the map, hopefully, meditating on it. You have a query point. Tell me at which face I am. Where did this map come from? Maybe it's a real map, states, and so on. Maybe it's Voronoi diagram. Maybe it's Delanoy triangulation. Maybe it's a free space of a robot. My robot just landed here and wants to get to another point. Tell me in the free space how to get, and so on. So we have this map, preprocessing it, hopefully with as little memory as possible. And so that I'll give you a query point, and you'll tell me where this query point, which face contains my query point. Okay. And hopeful, better than log n is not very realistic for, as usual, for general data, not data without log n is usually lower bound. One of the questions that I ask you, a variant of it, is that you have a set of points and you have a set of segments, and I want to find for every point what is the segments above it, for example. Or I want to find what is a segment below, or to build a trapezoidal map that we'll see. I'll remind you in a second what it is, which was just a line strip line sweep for every times that you hit one of these points. You are checking what is the segment just above it, and segment above it know on which face it's bounded. So if you keep the status of the line sweep, which face do I keep, which segment is above me, you are covered in terms of answering the query in linear time. And if you have batch query of a lot of query points, then you can do it. If you know what the query points. Ahead of time, it's close to linear. By the way, I assume here that segments don't cross. It's a map. If there are segments that are crossed, I already made them into two different faces. OK. Let's use this idea about the line sweep a bit more. So what I do here in this warm-up exercise is from every vertex, I shoot a line all the way down, all the way up, from infinity to infinity. And I do it from each and every vertex. I don't miss any of the vertices, which implies that inside I subdivided the plane into slabs, into strips, such infinite strip. And inside the interior of the strip, there are no vertices. And remember, my segments don't cross. Implies that inside a slab, the order between the segments is the same. The order of the segments inside a slab is the same. So inside such a slab, let's highlight it. Don't have much luck with markers today. Here is my slab or strip. And remember, I already assumed that there is no vertex inside it. If there was any vertex, any endpoint of one of the segments, or crossing between segments, I would push another vertical line, like so. So inside the slabs, all my segments crosses it from left to right. I don't have any segment that starts inside the slab. So if I'll give them names S1, S2, S3, store them in a search tree or an array or whatever. And now I'll give you a query point, Q. And you will ask yourself, hey, Q, among all these segments, S2 is a middle one. Is Q above or below S2? The answer is it's below, so I'll go to the left subtree. Ask is this above or below S1, above or below. Exactly like in the line sweep discussion, I don't keep the y coordinates of any one of the segments directly because different points inside the slab has different value of y and the segments are changing. I just keep the sorted list of segments inside the slab. Okay, and then I can do the search in log n time, the moment that I know what is a slab. And if I'll keep all these slabs, I'll take all the x coordinates of all these points and build a search tree. And from every interval of the search tree, I'll know to which slab I'm looking for, and I'll keep another tree sorted by y, and then in 2 queries of log n time, you can give me the answer. So that's one way to answer the point query slab, right? There are no vertical segments, general position. All edges are completely cross the slab from left to right. Nobody starts, nobody stops. And no two segments intersect. So in every such region can be sorted top to bottom, so bottom to top, and can do binary search. Time complexity. Again, annoying theoreticians. And slabs like horizontal, and segments like so. And if I keep for every slab all the segments that crosses it, I have n memory per slab times the number of slabs it's n square memory, impractical. Okay, so what can go wrong? The reason is that these two slabs are very similar to each other. Usually, especially if I'll assume no general position, between two consecutive slabs, the only difference is that in one segment it started or stopped. Okay. Constant number if it's a map, if it's just segments, it's either a segment that just started or a segment that just stopped. So the tree for this slab, ti minus 1, and the next slab, ti are very similar. And one way to avoid this n squared time is to use a really cool data structure called persistent data structure. And this persistent data structure is a data structure that allows you to keep a tree that goes through changes. I take the tree, do an insert, do delete, do an insert, but somehow I keep all the copies of the same tree. And if you'll tell me this is the x value or the time value that you're asking for, I can access a copy of the search tree as it was at this particular time. You can think about it as cities that have birth events and death events, and I want to do a query like who are the names that start with CO, what's the smallest lexicographic part, but people are getting die or born, and I can keep all the copies of any search tree with very little overhead per every insert or delete. It's called persistent data structure. Worth looking at, not in the syllabus. Okay, that's one way to solve it with less than n square memory. Somehow, right? Because when you're thinking about what is the difference of the search trees that defines for this lab and the search trees that defines for the next lab, it's only accessed in like log n changes. If I can do an insert in log n time, then the amount of changes that I can do in log n will be only log n many pointers have changed. Most of the trees are recyclable. Instead, we are going to discuss trapezoidal map and data structure for trapezoidal map. So, trapezoidal map, we talked about it already. Let's talk about it again. From every vertex, I shoot a ray downward until I hit one of the other segments, and then I stop. I'll do it also for the top. I'll keep all the segments in some big rectangle R, so it wouldn't go to infinity. At worst, I'll go all the way to the bottom of R or the top of R, just for to have some starting position. Okay, so from every vertex, shoot a ray up, shoot a ray down, but stop when you hit either boundary of R or you hit another segment. And we discussed it already. It defines a set of trapezoids. Why trapezoids? Because each such creature, well, some of them might be triangles, which is type of trapezoid. But if it actually has 4 edges, if it's quadrilateral, then the right wall and the left wall, general position, are both extensions created by vertical rays shooting up or down. Right? So these two are parallel. The floor and bottom are not necessarily parallel to each other. General position would mean they never are. Okay, so this is a trapezoidal map. I'll assume segments don't cross. I'm scanning through it because we have seen it already. And let's assume general position. And every face now will be a trapezoid that have, well, 4 sides. How are they? There are different types of trapezoids depending on each wall. A wall might be created by either an endpoint of a segment that I shoot away upward, or here is an endpoint of another segment where I shoot ray both downward and upward, but it still defines a one trapezoid. Okay, that's how the left and right wall and the bottom and top are one of the input segments. So notice that I completely forgot about it being a map. From now on, it's just becoming a set of segments that don't cross. So each face has either one or two sides, and they are exactly two non-vertical, one at the top, one at the bottom. Why is this the same segment? Because if I had the endpoint of a segment somewhere here, I would shoot away from it, splitting this trapezoid. Okay, and yeah, and of course, each such face is a convex trapezoid, by the way. Don't know of any other ones. And each such face has called the will define formally the top and the bottom sides of the trapezoid, the two segments of the input. Okay, so from now on, I'll assume that the faces are somehow vanished, and every segment knows to which face it belongs from the big map. That is, I don't care that the segments come from a map or not. How many trapezoids did I generate? We can look at it in a few ways. One would be that how many events do I have when I'm doing the line sweep? And I have a set of segments. Then each event was an endpoint, and I created one way upward, one way downward. But the moment that I hit other segments, I stopped. So if there are only n events, then there are only n trapezoids. But since we are going to use it, let's look at it a bit more closely. I have two n endpoints of the segments. No two happens in the same x direction. Each endpoint can create 3 vertices and 4 corners. How can an endpoint create a corner, or a corner of a trapezoid? Here is my segment, Si. I'll shoot away until I hit one trapezoid. I'll shoot away until I'll hit another one. That's one case. So this endpoint creates a corner of this guy, a corner of this guy. Make sense? And similarly, this endpoint, shooting it to the upper side, creates a corner over here. So at most 4 corners. Think about all the cases. Am I going too fast? Is making sense. Just think about an endpoint of a segment. Think about the vertical decomposition. Another name for the trapezoidal map is a vertical decomposition from each element. Shoot your way up, way down until you hit something else. So each vertex, each endpoint of a segment can create at most 4 corners. There will be the trapezoid that is from this endpoint just above and to the left, trapezoid from the right and below, and depending on other segments, how they behave, there will be at most 4. So if this is the number of corners, then everything is linear. Euler formula once again. Euler formula, for your memory refreshment, the number of vertices in every map after the trapezoidal, the vertical decomposition, easier to say vertical decomposition than trapezoidal. After the vertical decomposition, each vertex, now I have new vertices at certain points, but the number of vertices, essentially I created a planar graph, right? How many faces do I have? Now every trapezoid is a face, but the number of faces that I created, the number of edges, including segments, including trapezoidal map, including segments that now needs to be split into subdivision. Right. Now when I consider the trapezoidal map, then here is S1, S2, S3, and S4. And when I think about S1 and create a vertical decomposition, then S1 now is split into multiple pieces. This would be one piece. This is another one. This is another one. So it is split to multiple places. But all in all, because it's a planar graph and it has only linear number of vertices, you also have linear number of faces, linear number of edges. linear in the number of segments. We are going to rely quite heavily on this part. OK, so now I have all these trapezoids, and I want to at least tell you about the data structure. Every trapezoid will know who is on its left, who is on its top, bottom. Top and bottom are always input segments, and the left and the right walls of the segments. And the wall should know, like similarly to DCEL data structure, if I'll go from the left of this trapezoid, then all I care is, am I above or below this point, which will tell me either this is on your left or this is on your left. So your left neighbors, if you ask delta 3, who is on your left neighbor, it will say on my left side I have 2 trapezoids. General position will mean no more than 2. I don't have another point exactly in this x coordinate, so left of delta 3, there is either delta 4 or delta by itself. So only 2 neighbors from the left side, the same from the right side. And above and below will be a bit harder, so I don't bother storing it. I'm not telling for a segment who is below you and who is above you. And why can I get away with this? We'll see. OK, so finally, what is a data structure that I'm going to create? Just to rehearse so far, I had a set of segments. Possibly this set of segments came from a map. I have exact faces. I have 3 faces, F1 in infinity, F2, F3. Each one of the segments know to which face it is. Or just segments. My problem is, given a query point, pre-process all these segments, the map if you wish. But from now on, it's just individual segments. And pre-process it so that I'll give you a query point, and you'll tell me at which face I like, which trapezoid contains me. I don't care about the individual faces anymore. Individual face, because of the vertical decomposition, this individual face has been split into 3 trapezoids. I cheated a bit by drawing 2 lines, but general position would mean they are not exactly one above the other. OK, and these 3 trapezoid says I know at which original face of the Voronoi diagram say we like. OK, query, 1 point, Q, and I need to know, hopefully fast, what is a face that contains me. And actually a very practical query. So we talked about trees, but no, we're not going to build a tree right now. We are going to build a DAG. Not surprisingly, quite similar to what we have seen in the case of the Lanois triangulation. It's not the first DAG that we see. But now our DAG will be a bit different. DAG, directed acyclic graph. Guys, 10 more minutes. 7 more minutes. So in the DAG, we will have 2 types of nodes. X node corresponds to an endpoint of a segment. You'll see an example coming up. X node just keeps about endpoint of the segments, and the query with respect to such an X node would be, am I to the left of this X node, am I to the right of this X node? Y node, on the other hand, notice that they are not symmetric. There are not 2 types of, they are not analogous to types of nodes. Y nodes are very different. Y nodes stores the whole segment, the segment that they correspond to. I will ask, am I above or below this segment? Actually, I'll ask, am I above or below the line that this segment's defined? But it will be with respect to a segment, not with respect to a single scalar, a single number. Quick example. Here is a trapezoidal. Here, the input here are just the 2 segments, S1 and S2. I put the big box R around all of them. And I created the vertical decomposition. From P1, I shoot a ray up, ray down, created a trapezoidal A, which is actually a rectangle. From P2, I shoot a ray up and down, created this trapezoidal C, B over here, D, F, E, and G. Okay, I mean, everybody is cool with the left side of this slide? How did I create a different trapezoids? Still not the data structure, just how each trapezoid is created. Why F is not split because of Q? Why F is not split due to Q? Because Q shoots a ray downward, but this ray hits S2, so the ray does not continue. That was the difference between the slabs versus the vertical decomposition. Good. And here is a data structure that our algorithm will build to enable point location in this trapezoidal map. Remember, my query point will lie here. I need an answer. It's inside E. My query point is here. I want an answer. Is this inside F? And you see that it's not a tree. Here is F, the trapezoidal F. It's a leaf. And I can reach to F from a few directions. I can reach to F both from this side or from this side, and that's OK. It's not a tree. Also notice that S2 is stored several times in this DAG. That's also fine. Let's see how it works. Q just landed on us. We will just announced about this query point Q. And let's work on it together. What would be the search path? Remember two types of nodes. Shaded one are the Y nodes. Are we above or below the segment? White ones are we to the left or to the right of an endpoint? We don't care about the height, just left or right, just X coordinate. Let's think about the search query from Q. Let's work on it together. X node or Y node? X node. Shaded. Q over here. To the left of P1 or to the right of P1? To the right. Right? If we were on the left of P1, we would end up in A, as it should be. That's the only trapezoidal that is to the left of P1. We are on the right of P1, so going over here. Q, above or below left or right of Q1. It's an X node. Q1, 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 left of Q1. So go to the left. Where did I buy this? So go to the left. Now, finally, we have a Y node, the segment S1. Notice if I was above S1, above S1, then I would say I'm inside B. Since I'm below, sorted from bottom to top, since I'm below, then I'll go to P2. I'll go to P2. I am Q to the right of P2. So now so far, I'm down to either I'm in D or in F, one of the two. How do I know if I'm in D or in F? I need to ask, is Q above or below D or F? OK? Since I'm below, I'll go to the right. Y value is highlighted, animation that I stole. OK? And notice that I could have, if Q was here, then the search path would go still to F, but through a different path. OK. So we need, everybody is cool with this data structure. And that would be the famous DAG. And we had similar idea in the when we created the Delanoy triangulation. We had old triangles which were replaced by new triangle, and we kind of go through the same way. And if you remember, we are just adding the segments one after the other. And the data structures that we are going to use at the end, that we are going to produce, we're actually going to have the same data structures that will stay with us for each new trapezoid. How many changes do I need to have in the whole data structure? Let's see. Let's say that here is set of segments, S1, S2, dot, 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 Sn half. And now I'll add one big segment. Let's call it S prime 1. It's one big segment, and it hits all the trapezoids that I had so far, all these tiny trapezoids. And if I want to create maximum complexity, then the next segment that I'll add, S tab prime of 2, S prime 2, will just below, and now I have n trapezoids, n half trapezoids that I need to update. Lot of work, linear work to update. And now add S3 just below it, and still another n trapezoid. What saved us in the linear programming? What saved us in the Delanoy triangulation? Insert the points, but in random order, and argues that when I'll add one segment, it will only create a constant amount of changes in expected wise. Why only expected number of change? Why only constant number of changes? Because look at the segment. After you added all the segments, look at one of them. How many trapezoids lie on this segment? One segment can touch a lot of trapezoids, but on average, we have linear number of trapezoids, we have linear number of segments. Divide the number of trapezoids by the number of segments. Each segment touch, on average, linear number of trapezoids, meaning that if I'll add it at random, it will only create constant number of changes. Linear number of trapezoids divided by linear number of segments implies every segment, so this one, touch on average only n trapezoid. That's a number of changes that will happen if I add the segments at a random order. Good point to call it today. Thank you.